is a Canadian mathematician who did his PhD under the Bela Balobas in University of Memphis. Then he came to Brazil as the postdoc of excellence at IMPA under the supervision of Rob Morris. He works in extremal and probabilistic combinatorics, Ramsey theory, random polynomials and matrices, and combinatorial number theory. He was awarded lots of prizes, among them the European Prize in Combinatorics, the Salem Prize, and the Whitehead Prize, and of course the MCA Prize of this year. It's a pleasure to ask you to welcome Julian to talk to us.
Hello. Okay, thank you very much. It's a pleasure to be here in front of you and to talk about some, what I find to be some really fascinating mathematics and some puzzles that are really deep and confusing for us in extremal and probabilistic combinatorics. This talk begins with a bit of an apology in that I have to say I'm not the greatest slides person, so you'll see it gets a bit arts and craftsy as we go in. Okay, so I'm going to be talking about the Ramsey numbers, and many of us have heard already the main concept behind Ramsey theory, that complete disorder is impossible. For these very large systems, we have very structured subsystems. What I'd like to talk to you today about and try to convince you is a really interesting subject is what's been the more modern study of this, which is the quantitative aspects of this. How big do you have to be before you start to see structure? And how much structure? And this is, to me, an extremely fascinating question, and I hope to say something about it. Okay, so let's start at the beginning here. And in some sense, this is a bit of a stupid problem, but I think it's a good place to start. So this is sort of the place to start for Ramsey theory. I have 6 points that I've drawn here, and I give you a blue and a red pen, and I allow you to draw, color the pairs between these 6 points and however you like. Okay, so here you fill it in like this. And I claim to you that no matter how you do this, no matter how you fill in these points, you'll be forced to have a monochromatic triangle. So what do I mean monochromatic? All edges are the same. So here we see there's a monochromatic triangle, all blue. In fact, there's another one here. And so you are forced this no matter what. Okay, so there's your monochromatic triangle. On the other hand, if I put down only 5 points, I'm able to color them like this so that there's no monochromatic triangle. So you can check there's no triangle here. Okay, so in some sense, this is a bit of a stupidity, just like some small example, but let's prove it, because we'll see it really actually has some legs as we go further. Okay, so in my other page, I'll prove this result that any way you color this guy will have a monochromatic triangle. Okay, so I have my 6 points. I'm going to just pull 1 point aside. Any point, doesn't matter. And that point will be joined to the rest and either have 3 red edges to the rest or 3 blue edges to the rest. Okay, it could have more, but let's say that. The colors are symmetric in this case, so let's just call them red. So it has these 3 red edges. And now note that if I color any of these pairs red, then I'm going to have a red triangle. So I'm forced to color them all blue, and now I have a blue triangle. Okay, so this is a proof that any coloring on 6 contains a monochromatic triangle. And 6 is actually enough. Is the best possible. Okay, so as I said, this is kind of a silly thing. But what's really interesting is that it goes further. So it turns out if I were to put down 18 points and ask you to color all the pairs between these points, I can actually find 4 points and among that 18 such all the pairs between them are the same color, are monochromatic. And the same holds when I replace 4 with 5, 6, and so on. And this is exactly where we begin with the Ramsey numbers. So R of k, this is the kth Ramsey number, is defined to be the minimum n, such that so that's the number of points, so that every red-blue coloring of kn, so kn is actually the complete graph on n vertices, the set of all pairs on that 1 up to n. contains a monochromatic k sub k. So with this little doodle that I had here, I actually proved to you that R of 3 is equal to 6. So 3 being triangle, 6 being the number of points. That's the smallest number possible, and it's bigger than 5 because of this example. Okay? So these are the Ramsey numbers. These were defined in the 1930s by a really fascinating character, Frank Plumpton Ramsey, who was in Cambridge as a student, and then, that's his real middle name, who was in Cambridge as a student, and then as a postdoctoral fellow. And he actually died at 26, but already made contributions here to Ramsey theory, but also to economics and philosophy. It's really incredible. But of course, here we're interested in his contribution to mathematics, where he defined these R of k and showed that they exist for every k. Right? So it's not actually obvious that they exist at all. And Ramsey, really, I say a theorem, but really it was a lemma of his towards something else. Okay, and we'll see a proof of this in a second. Okay, so this is 1930. He unfortunately died in 1930. I think this was proved in 29. I'd also like to talk about Erdős and Szekérys. So a few years later, they actually independently discovered this same result. So this is a young Erdős on the right, quite strapping young fellow, and George Szekérys on the left. And they independently actually discovered these numbers and gave the first sort of like good quantitative upper bound on these numbers, first exponential upper bound on these numbers. Okay. And this really, in a sense, begins our modern study, because I'm really interested for the rest of this talk, how does this sequence of Ramsey numbers grow? And while it seems like a bit silly, it's only a single sequence, it really contains a huge amount of combinatorial information. And when we see the kind of ideas that have come to bear on this problem, well, we'll see there's actually quite a bit in this one sequence of numbers. Okay, but to start, I'd like to start out by proving to you this bound of Erdős and Szekérys. From the 30s. Okay, so what does this mean? It means that for every coloring, when I put down 4 to the k vertices, I can find a monochromatic clique of size k. Okay, so here we go. Get ready for the arts and crafts. Okay, so here's my coloring on n vertices, and you've gone in and colored all the pairs in this blob however you like. And my task is now to find this complete graph. So what do? I'm going to take a vertex inside of in my coloring and pull it aside. And now I'm going to look at how this vertex is joined to the rest of the world. Okay, so we'll be joined to some guys in red, some guys in blue, and I'm not interested in what's happening here. So I'm just, what's happening here? Okay, so one of these two collections will be at least 50%. Let's say the left-hand blob here is at least 50% of the world, the red blob. Now what I'm going to do is just throw away all of the blue and zoom in to the red neighborhood. And I'm going to keep that red vertex aside to be part of the first vertex in a red clique. And I keep doing this. So we'll go into this blob, pull it aside, and what do I get? So what does a general step of this algorithm look like? Okay, it looks something like this. So this here is my fistful of red vertices so far. So everything is joined inside of here in red. And joined to everything. This is my reservoir of things that I still have yet to explore. And I have a blue clique that I've built up so far. Those are from all the blue steps. And it's joined to everything in blue. And of course, if I can make one of these have at least k vertices, then I'm done. Okay, so what does a general step look like? Same as the first. I take a vertex in my reservoir, pull it aside. It's joined to some things in red, some things in blue. Let's say blue is at least 50% this time. So now I'm going to throw away everything here in red and put this vertex into my blue set. Okay? So this is at least 50% of the world. And notice when I do this, I preserve this picture. That I change the sizes of things, but I preserve this picture. And how have I changed the sizes? Well, I've shrunk my reservoir by at most a half, and I've increased either A or B by 1. Okay? So let's do a little bit of arithmetic here to see what number I get. So I started with n vertices down here. It's a bit lower than I thought. And at every step, I halved my reservoir. And how many times am I halving my reservoir? Well, I have it at most k times for my red clique, because I put at most k into the red. And I have it at most k times for my blue clique. And all the while I'm doing this halving, I want to make sure that my number of vertices doesn't bottom out. So there's at least 1. OK, so that means that the number of vertices, if it's at least 4 to the k, my algorithm won't, I won't run out of space, and I'll be able to either find a red clique or a blue clique. OK, so it's just some sort of greedy algorithm that we run. And this exactly proves Erdős-Szekerich's bound. There's actually one tiny cheat that I did, but I'll let you think about that. OK. So I've given you this bound just out of nowhere, but you don't know anything about what it's connected to. So really the next obvious question, what about lower bounds? Is 4 to the k a good bound? OK, it seemed like some sort of natural greedy algorithm, but what about constructions? OK, so I'd like to give to you if I gave this as a problem to you, the thing you would think of in the first 30 seconds, I'm sure. So let's start there. So what does it mean? Let's just go back for a second. If I want a lower bound on this quantity, what does it mean? I'm trying to build a coloring on the complete graph, and I want this complete graph to have as many vertices as I can have. OK, so here comes the coloring, really the first thing you think of. So take my set of vertices and partition it into a bunch of blobs of size, k minus 1 blobs, and each blob will have size k minus 1. Okay? And then inside each blob, I'm going to color everything red. And then between every blob, I'm going to color everything blue. Okay? So I claim this has no clique of size k, monochromatic clique of size k. Well, if it was red, then it better be entirely within a blob, but there's not enough space, only k minus 1 points, so no red clique. If it was a blue clique, you better have each point in a different blob, but there's only k minus 1 blobs, so there's no blue k sub k. So what does this prove? This proves a lower bound of k minus 1 squared. That's the number of vertices in here. OK, technically plus 1, because the Ramsey number is like the smallest. OK. So this is like quadratic in k. And that's not so good compared to our upper bound here. So there's one is exponential, one is polynomial. OK, so if you lived in ancient times, like this was 30s and 40s, you look at this in the following way, right? So here I showed you this essentially trivial upper bound. Right? I just greedily plug away at my graph, and I find a clique if it has 4 to the k vertices. And on the lower bound, I get this k squared business with a very natural construction. So it seems reasonable, as people did in ancient times. They thought that maybe k squared, a polynomial, is actually the right order of growth. So it came as something of a surprise when Erdős in 47 proved it was actually exponential type growth. OK, so now today this is completely, it's our bread and butter, this result. But I want to say something about it, because this signaled the sort of shift in thinking that happened in probabilistic combinatorics and in Ramsey theory. And the idea here was, instead of trying to construct like coloring as we did before, in these sort of naively building up, saying, I'm going to color this red, this blue, in some structure, instead to sample a coloring at random and show that in that big pile of colorings there exists some coloring that forbids cliques. OK, so the proof is very simple. I can fit it just in 2 lines here, so let's quickly do it. OK, so I want to color the graph on 2 to the k over 2. Never mind that it's not an integer. And now just choose a coloring uniformly at random. So I flip a fair coin for every edge, red or blue. And now instead of, I just want to look at the probability that there exists this monochromatic k sub k. And if I can show this probability is less than 1, then I'm just done. because that means there exists somewhere in this big patch of colorings a coloring that has no mono k sub k. Okay. And this is actually an easy business to compute, so, or at least upper bound. You can actually compute it as well. So there's n choose k possible monochromatic cliques, right? So I just union bound over each possible one, and I ask each possible clique, what's the probability that you're monochromatic? Okay, so here it doesn't really matter. I just chose the first, lexicographically first monochromatic. It doesn't matter. So this is just all pairs on 1 up to k, this confusing notation. Okay. But actually now, this business is actually very easy to compute. Once I've fixed my clique, what's the probability it's monochromatic? Right? So it's either just choose a color, either red or blue, and now all this k choose 2 pairs better can't come up the same color. So this +1 is for the 2 colors, and this is 2 to the minus k choose 2. All my coin flips had to come up the same color, and this is the probability. And now it's just some nerdy fact that this thing is less than 1. Okay, so just by a little bit of mathing, I can do this is at most this. And now we remember what n is. N is this 2 to the k over 2, which is exactly canceling with this 2 to the k over 2 with a little bit of room to spare. Okay, whatever, it's just some exercise, check that it's less than 1. And this is it. This is the proof. I also wrote here, if you analyze a little bit more carefully, this is the bound that you get. So this is I've just analyzed the expression a bit more carefully for lower order terms. So still the same dominant term. And amazingly, all that's happened in the years since this is this square root 2 is moved upstairs. Right? So, and this is not for lack of trying. So it seems to be really challenging to go beyond this result. Okay, so that leaves us with the following state of affairs. We have this upper bound due to Erdős and Szukeres from the 30s, 4 to the k, and a lower bound of 2 to the k over 2 by Erdős from the 40s. And you might think, okay, now we're basically done. It's exponential, they're finite, they're exponential growth. This is a nice conclusion to the story. But I claim there's actually a lot of interest in what's happening between these two numbers. And there are a lot of interesting mathematics. So for example, if r of k was a little bit more like, say it was something more like 2 to the k over 2, that would mean that the best colorings are actually random-like. Right? Or conversely, to improve this lower bound, you would like to find some sort of colorings that look random-like in many ways, but are somehow more rigid than random, somehow more special. And in some ways, it sounds like such coloring should exist, right? Random was sort of, from this point of view, seems like a very crude thing to do. We should have sort of more special constructions there. But on the other hand, maybe somehow it's just over-constrained, this problem, and you can't do better than random. On the other hand, to improve the upper bound, and this is what I'll talk more about, you sort of need to show that, your coloring can't force you to switch colors as this Erdős-Szukeres algorithm runs many times. So if you, as we'll see more in a second. So this sort of improving the upper bound is sort of like getting the global structure and the local structure to communicate a little bit better in the coloring. But I'll say more about that in a second. Okay, so let me just say something about the progress that's been made on these numbers since these results. So I've actually said everything that's known about the lower bound at this point. So let's talk about the upper bound. So I actually lied slightly to you. Erdős and Szukeres have a slightly different argument that gives a little bit better bound. So we actually have this square root. Okay, it doesn't move the exponent at all, but improves it, the bound a little bit. And this is basically where the situation stood for a long time until the 80s. And really the whole area of Ramsey theory, due to people like Erdős and Szekeres and others, really blossomed in this period. So it's not, it wasn't an obscure problem at all, but it took until the 80s to get any kind of improvement. And Rödel just stuck an extra log factor into here. And independently at the same time, Andrew Thomason, well, my hair's falling apart. Andrew Thomason improved the polynomial factor here. And then this idea, so I should say, so it's maybe easy to look down on these results because it's such a small improvement compared to the gap here. But this is actually the beginning here of quasi-random graphs, and a really important idea that's had a huge amount of impact in graph theory and beyond the early work of Thomason. And basically what he's doing is he looks at this Erdős and Szekeres argument and says, okay, look at the graph that I had in my reservoir at some point. Okay, if this graph is quasi-random, then I can say one thing, use some arguments from a theory that was sort of built up there. If it's not quasi-random, then what I can do is, in particular, say there's too many triangles, and do basically take 2 red steps in a row, or say 2 blue steps in a row. So you're either doing quasi-random or something else, beating the Erdős-Szekeres. Now this idea was pushed quite a bit further by David Conlon in 2008, who improved Thomason's polynomial bound to something super polynomial. So still not exponential, but now this business here is sort of decreasing faster than any polynomial rate. Again, building up this quasi-randomness sort of perspective. And then recently, this quasi-randomness was improved. This little o1 was removed by Saw a few years ago. Okay, so this is kind of where the story was when we got to it. And along with Marcelo Campos, Simon Griffiths, and Rob Morris, we were able to obtain an exponential improvement upper bound for the diagonal Ramsey numbers. Okay, so, well, this is a result that we were quite pleased with proving. It was the first time an exponential improvement happened since the work of Erdős and Szekeres. We had some shortcomings with our result, things that we weren't quite satisfied with. So, first of all, something that was a bit disappointing is that our result didn't generalize to more colors. So I've been talking about red, blue, but it's also just as natural to consider red, blue, green colorings, right? In general, we'd like to talk about R colorings of the graph and try to find a monochromatic clique in these R colorings. And you would think that a natural proof of this should generalize to more colors. So this was a shortcoming. So it does actually say certain things about the off-diagonal multicolor Ramsey numbers, but it doesn't get the big question about what's happening on the diagonal. A second shortcoming is when we were thinking about this problem and thinking about how to improve the Ramsey numbers, we were really guided by this sort of geometric intuition. We had some kind of geometric ideas behind what we were thinking about. But in our final paper, that was all kind of lost in the wash. We sort of needed too many, we needed too many aspects of the exact application. And we were a bit disappointed that this sort of exciting intuition that we had from geometry was completely lost at the final paper. And okay, and third, and sort of maybe most personally to us, we felt a little bit like maybe we got lucky. Okay, I mean, one has to always be lucky in order to do mathematics, but it felt lucky in the following sense. So in order to understand these Ramsey numbers, what we first did is we understood the off-diagonal Ramsey numbers. I haven't defined it, doesn't really matter, but some other related objects, the off-diagonal Ramsey numbers. And then we improved the off-diagonal Ramsey numbers. Okay, so I claim that that wasn't lucky at all. But what was lucky is we could run a different algorithm, or a modified version of our algorithm, to relate the Ramsey numbers to the off-diagonal, but at a loss. So we are actually doing worse in the Erdős-Szekérys to get from the diagonal to the off-diagonal. But then running our improved algorithm on the off-diagonal to get a victory. So, and the whole point is that the win from the off-diagonal countered the loss from getting from the diagonal to off-diagonal, and we were able to declare this improvement. But it's not so clear. I mean, you can sort of look at it and convince yourself that there should be this win, but it's not so clear that that should work as a strategy. Right? So we'd like something that more directly and is clearly showing that we're winning over Erdős-Szekérys, really directly improving. So this is maybe a third reservation, if you will. Okay, so this was now a couple years ago that we put this paper out, and not this spring, but the last spring, we got together and tried to sort of rehash our approach, tried to reinvent our geometric understanding, and maybe try to satisfy some of these shortcomings. And then we got together, so the original group got together with some other guys that we like to work with, and tried to put the pieces together for this new approach. And with this, we were able to prove an exponential improvement for the multicolor Ramsey numbers. Okay, so let me just explain what's written here. It'll take a few minutes. So for every r, so this is the number of colors here. So already is interesting for r is equal to 3. Just three color Ramsey numbers. We couldn't prove that with our previous paper. Okay, but now we can do it for all r. There exists some delta so that the r color Ramsey numbers, so this is now, I'm allowing you to color with r colors, is at most, okay, this is what the Erdős-Szekérys bound gives. I'll say more about that in a second. And we get an exponential improvement over it. There should be a sub r here. Excuse me about that. So we get an exponential improvement for the r color Ramsey numbers. So we're now feeling happy that this does indeed generalize to more colors. But the proof, as I'll try to get to in a second, regains this connection to geometry. And in fact, my goal of this talk is really at least just to touch where this comes into it. You have to be sort of into the details here. And finally, we think that this proof is much sort of clearer, and we stay on the diagonal. It's much more straightforward, the comparison to Erdős-Szekérys, and we don't do any of this funny business where we're moving from the diagonal to the off-diagonal. So of course, it's for you to evaluate, but it feels like this is it's very clear why we're winning and less like a lucky fluke. Okay, good. Okay, so I said something about these Erdős-Szekérys, the multicolor Ramsey numbers. Let me just say one sentence about the history here, because it's a bit negligent for me to say nothing of the history. So here's the one-line history lesson. So the upper bound was prior to our work. This was the best known thing. So this r to the r times k. And this is actually the immediate generalization of the Erdős-Szekérys argument. So notice, of course, if you put 2 in there, you get exactly 4 to the k. But it's the same argument that gives this as well. So this r here, right, if we just imagine running the same argument, my vertex has r colors joined to my reservoir. So I take 1 over r proportion of the world. And now I have r different fistfuls of vertices that I need to keep track of. So I need to run the algorithm for r times k steps. So it's just the immediate generalization of what we saw. You can write it down in 30 seconds. The lowered bound is actually a bit of a different business here. And the best known is this some constant times r to the k. And this goes back to the 70s due to the work of Abbott. But as recently, the value of this constant has gotten pushed up a bit by work of Conlon and Ferber, Yuval Vigdorson, and Will Sawin. And it's also, this is a good point to mention, this is another big mystery in Ramsey theory. So you notice here we have an exponential bound in Rk, and here's something super exponential as r is getting bigger, as r is going to infinity slowly, say. What's the right order of magnitude? Right? This gap is growing, and it seems to be really unclear what's the best thing. And it's a real mystery as to what's happening. Okay, so our result now gets an exponential improvement on this. You might hope that as this gap is growing, our delta is actually getting bigger as r gets bigger, but it's not, it's going to 0, okay, but not too slowly. So it's we make an improvement here, but there's still a big mystery as to what's happening. Okay, so in the time that's left over, I'd like to say something about the proof of our upper bound on the Ramsey numbers. And in particular, I'd like to try to sort of get to the point where you see the connection with geometry and might get your geometric intuition going. So that's what I'm going to do. So what I'm going to talk about is an algorithm, and I'm going to have a bunch of nerdy pictures on the board that are quite specific. But we're going to try to understand this algorithm and what makes it run, and we're going to get to some really interesting mathematical questions, I think. Okay. Also, I'd like just to talk about two colors. Our new proof now gives a new proof for two colors. And the nice thing about our new proof for two colors, it immediately generalizes in the most natural way to our colors. So I'll talk about two colors, but you won't be disappointed. I'm not talking about more colors, because the first idea you have for generalization actually works. Okay. So let's go back to this picture. So this is my little Erdős-Szekérys picture. And in order to understand how I'm improving the Erdős-Szekérys numbers, we have to understand where this picture is lossy. So where am I losing in this picture? And the sort of maybe most obvious place you're losing is the following. So I was building up this clique in my left hand over here, or a clique over here in my right hand. But at the end of the day, I only needed one clique, right? So I only needed one monochromatic clique. So I had to pay for all of these red steps, even if I ended at the day with a blue clique. So what we'd like to say is look at our graph and say, actually, all I want to do is take red steps in this graph, and hope that I don't run out of red space. And this is exactly the kind of thing that we're trying to do. We're not going to take only red steps, but we'd like to take a large number of red steps, sort of all in a row. What does that look like in terms of a graph structure? It looks like the following thing. This picture's sort of dorky. Okay. Which is this little structure, which is called a book. Okay, so I have a clique here, and I'm going to want this to be like, have t vertices, where t is like a constant times k. Okay? And each one of these steps halves the world down here. So everything here is joined in red, and everything here is joined to this in red, but I don't know anything about the colors here. Right? I've just extracted this from the Erdős-Szekérys picture. So this is called a book, for whatever reason. Right, so, and I want to ensure that this business here is at least at most having it at every stage. Okay. And this is basically the object we want. I'm actually doing a little bit worse than having it, but I don't want to get into those details. Okay, so what I want to do is build one of these things. And to do this, we introduce the so-called book algorithm. And here is this complicated picture, which I like to just stay with me with this. So it's a little bit of a complicated picture, but we'll see the interesting business in a second. So this is a little bit like this Erdős-Szekérys picture that I want to maintain as the algorithm goes along. Okay, so I partition into these 5 bits. So this A up here, I'm going to say is joined, is a clique here, and joined to everything in this Y sub r in red. This is my red book so far. Okay? On the other hand, I have this, also we have that it's joined everything to this x, and as before, this x is like my reservoir. This is where I'm going to add vertices to my either clique. Okay. I'm not really going to motivate this picture and where it comes from, but we'll just sort of play with it and see what happens. Okay, and then downstairs I have the symmetric picture. So I have my blue clique down here. Okay, that's joined to everything. Sorry, this is my blue book rather. So the blue clique joined to everything here, and symmetrically it's joined to everything in the reservoir. Okay, so this is the picture that I want to preserve. In fact, I want to preserve some other features of this picture. But let's just imagine this is what we're given. What I want to do is take a vertex and see what it would mean to put it in either to the red clique or the blue clique. Okay? So let's take a vertex outside of my reservoir. And as before, I'm going to investigate the neighborhood here, the red neighborhood here, and the blue neighborhood here. Okay, so this is a more complicated picture. Let's just assume, for whatever reason, I want to take this vertex and put it into my red book, this red book up here. What would that mean? What would I have to do for this? Okay. Now, if I put this vertex up here, I would have to shrink in order to maintain this picture. I would have to shrink this set to be the red neighborhood of this vertex. I could even shrink it more, but I certainly have to at least shrink it in order to maintain this property. Okay? On the other hand, I also have to make sure, in order to keep this property that this is a book, I have to look at the neighborhood, the red neighborhood over here. So I've drawn here the red neighborhood. I just didn't want to draw the red vertices here, the red neighborhood. And I need to shrink this y sub r to be the intersection with this red neighborhood over here. Okay. And now here we start to really approach the juice of the matter. So the first thing is the degree of this vertex, or the number of red neighbors over here, better be about 50%. Right? So it's a little bit more complicated actually in the paper, but just sort of naively, we expect it to be about 50%. Because remember, with this book, for every step that I take, I want to at most have the number of vertices in my book. So it has to be about 50%. Okay, for now, let me even grant you that the minimum degree of everything in here over here is about 50% of the vertices. I'll even grant that to you. Okay. Sorry. But now we actually see the real problem. Is say I take this vertex, I shrink this, I move this here, and I shrink this. What if the red edges between here and here, the density of red edges between here and here, drops by quite a bit? Right? These are just two subsets, one on the left, one on the right. Even if I grant you lots of good information about the density across, what if for whatever reason the density between here and here is much smaller than you expect? Okay? And this could be a really big problem, because if the density drops significantly, then in the next stage, the degree of a vertex into that world is much smaller. So then you're eating up much more of the right-hand side. And what if the degree drops more? It could really cascade, and you get nowhere close to this. So you really have to hold on to the density, the red density across. Of course, everything I'm saying here, ditto for taking a blue step, but let's just focus on the red step for now. Okay, so I'm going to redraw this picture. I just want to redraw the picture of x, my reservoir x, my vertex, and the red, the ends of the red book here. So here's this little picture. Okay, so what's the offending picture look like? I have this vertex that I'd like to take and put into my book, and I have to shrink here, possibly more, and I have to shrink here. Here you don't really want to shrink too much more. So the problem is, if there's lots of vertices y, so that when I look at the red degree across over here, so I even granted you that this is, say, 50% of the world here. So this is 50%, this is 50%. What's the problem is if this bit of the world is significantly smaller than 1/4. Right? Because when I shrink down to here and down to here, the density across will drop below 1/4. So this is really the kind of problem. And the way I like to think about this is it's like the neighborhoods of these vertices are sort of repulsing in space. Okay, so this is really there's a bunch of other details that I've completely skipped over. I've just sort of zoomed into really the main issue here. What if I have this property that when I take a vertex x, I look at its red neighborhood on the left, and lots of those vertices that it's joined to in red on the left have these repulsive neighborhoods. This is kind of the key combinatorial situation. Okay, so let's make a little definition here. Say that a pair of vertices on the left is good if their intersections with the neighborhood on the right is at least 1/4 minus some small epsilon. And here it doesn't really matter so much, but you can think of it as smaller than 1/k, basically because there's like constant k steps in the whole algorithm. It's actually going to be more complicated than that, but this is a good way of thinking of it. So say if it's good if this holds and the symmetric thing holds for blue. Okay, I claim that if this happens, then we're actually in really good shape. Why? Sorry, if I have lots of good pairs, say a constant proportion of good pairs, we can actually take a step and add to our book. So here's back to our picture. If I have lots of good pairs, take some vertex here that is in lots of good pairs, and now just reveal the colors between x and these good pairs. Say red is at least 50% here. Now I just take all the red neighbors that are good, and I take a red step. Because now if I take this little bit, shrink my x to be the red neighbors here, red good pairs, that means all of these neighborhoods interact nicely with the neighborhoods over here, and I preserve my density. In fact, I preserve my minimum degree, which is even better. Okay, so in other words, good pairs are, if I have lots of good pairs, I'm happy. But it's actually not at all clear that you have any good pairs, or a constant proportion of good pairs at all. And this is where we kind of get some idea from the geometric understanding. So we can rephrase this question in the following way. And this is where we touch the geometry problem. So here's it's not completely rigorously worded, but I'm hoping that it inspires, gets you thinking a little bit. Inspires your intuition. So say I have a bunch of vertices. So there's no graphs anymore. These vertices are encoding the red neighborhoods. These vertices over here are encoding the blue neighborhoods. But in fact, we can drop all of that. So say I have some vertices in R, some vectors in R to the n. The dimension actually doesn't matter so much. And another collection of vectors that have nothing to do with this collection, except that they have the same index set. Okay? So these are actually not talking to each other, except they're indexed by the same set. And they have this very funny property, so that all but some delta proportion of the pairs, we have either this inner product is significantly negative, or this inner product is significantly negative. Okay? So the way I like to think about this is I have two. It's nice to think of these points just on the sphere, so you're not confused by the scaling, or just rescale it so their typical inner product is like constant. So a sphere like that. It turns out the scaling is fine, but it doesn't matter. So I have these two sets of points on the sphere, on two spheres, one sphere here, one sphere here. Is it possible to pair them so that every time you have a positive inner product in one, when you map it over to the other pair, you get a negative inner product? Right, so somehow the correlations in one, positive correlations, are exactly mapped with the negative correlations in the other. In fact, it is possible to do this because you have this delta x squared pairs that you can throw away. So for example, you could take a simplex in dimension like 1 over delta, and then basically all the pairs will satisfy this. So just forget about those and build the simplex here. So say we have this, then you might hope that either this set is structured or this set is structured, in the sense that they cluster around a simplex or have some kind of lots of positive correlations. And this is the main new idea in our paper, is we can prove a version of this problem. So either you fail this property, which is the same as being good, having lots of good pairs, or you satisfy this property, in which case one of these two sets of neighborhoods is structured. And that allows us to take a third kind of step in the algorithm, which I didn't talk about, which is like a density boost step, which allows you to find a subset where you zoom in on the left, zoom in on the right, but you push your density up by quite a bit, which allows you to, which you can use later down the road in your algorithm. Okay, so I'll stop there. So I'll say thank you and just leave you with our main results from today. Thank you.
Thank you, Julian. Nice talk. Questions?
You mentioned that this delta is going to 0. Is that right?
That's right, yeah. As R goes to, R gets bigger, yeah.
And your hope is that like it actually like stabilizes, or yeah, what would be sort of the ideal situation in this in this case? Like what would be the improvement on the delta?
Okay, so a first improvement might be showing that you can get away with a fixed delta, so independent of R. But it's not even clear that, in fact, it seems quite reasonable that you should be able to get an R going to infinity, actually rather than 0, because of the lower bound. But there's sort of further obstacles in doing something like this, yeah.
And for like the, so I'm guessing like for R equals to 2, like you had the 4 minus C, sort of like the bound, and that's related to this like e to the thing. Like, is the C sort of explicit in your work, or like what's the magnitude I should think about? Like,
that's a good question.
At least in the R equals to 2 case.
Yes, so the C is actually explicit in our work, but then was optimized recently. So the state of the art is now like 3.8, I believe. So, upper bound is 3.8 to the K.
Okay. Yeah. Cool. Thank you.
Any more questions?
I think I lost something in your toy problem.
Okay.
There is no relation between Vx and Ux, right?
That's right, yeah.
So I could just take the same set.
That's right. But then if you have a positive correlation in one, it will correspond to a positive correlation in the other. So for lots of pairs, you'll have lots of positively correlated pairs if they're just the same. So you'll have lots of positively correlated pairs, so then it will be the same over here. So a way of thinking of it is like if you have a positive correlation in the one, it maps to a negative correlation in the other, which is the kind of weird property here. But yeah, I think it's a bit surprising that they don't talk to each other at all. The U of X and V of X, apart from they have the same index set.
Any more questions? Okay, if not, let's thank Julian again.
Thank you.